Hello there, this is Miss Nakayama, and today's lesson is 2.6a Rational Functions. So today we're going to talk about finding the domain of rational functions. We're going to use arrow notation, and then we're going to identify our vertical and horizontal asymptotes. So I know you have done this before. I know you've done asymptotes before. Arrow notation might be a little bit new, but let's refresh your memory on what a rational function is. If you look at the first 5 letters in the word rational, you see ratio, because rational functions are just quotients of polynomials. Okay, so it's just a fancy word for a fraction where you're going to have variables in the top and the bottom. Okay, so what you have to remember is that we've talked about before, the domain of that rational function is going to be all the values except those which make our denominator 0. So that's the key. You've got to remember the denominator cannot be 0. So when it says find the domain of a rational function, the first thing you want to do is set the denominator equal to 0. In this case, my denominator is x minus 5. Solve that for x equal to 5. And my answer is going to be, this says the domain is all real numbers x such that vertical line is such that x cannot be negative 5. This is set builder notation. What you've done in the past is interval notation that look like this, okay? But in your answer, I think y'all probably find it easiest. You only have to give this part of it. So look at it when you answer your questions in your homework. Okay, look at this example. Find the domain of this rational function. G of x equals x over x squared minus 25. So again, set the denominator equal to 0. In this case, x squared minus 25. Then we're going to factor it as the difference of two squares. That's going to give me x minus 5x plus 5. And that tells me that x equals 5 or negative 5. That means those are the numbers that make the denominator 0. So if I come down, when you put your answer into MyLab Math, it should have the beginnings, all of this already written for you. So all you have to put in there is 5 and negative 5. And you don't have to worry about the interval notation of it. Okay. All right, one more example, finding the domain. This time my denominator, I have x plus 5 over x squared plus 25. It is not, the denominator is x squared plus 25, but that is not the difference of two squares. So you might solve it by moving 25 to the other side, which gives you negative 25. And when you take the square root of both sides, you know that x equals plus or minus 5i, because when I take the square root of a negative number, then I'm going to have an I in my answer. So what that tells you is that there's no way to make this denominator equal to 0, or the denominator will never equal 0. Where'd it go? So that means your domain is all real numbers. Okay. In interval notation, we've written that in the past, negative infinity to positive infinity. Okay, so now we have to talk about our vertical asymptotes. So first off, the definition of a vertical asymptote is a vertical asymptote of a function is that value, if you have a point, the line x equals a, such that the function increases without bound as x approaches a. So here is x equal to a, x equal to a. And no matter which way I come at it, it's getting closer and closer to it. This function is increasing without bound. It's going on forever and ever. Okay, so this is how we write it. If it's coming from this one here, okay, this one is on which side of the arrow is that? Well, that's on the right side of our vertical asymptote. I said arrow, but it's on the right side of my vertical asymptote. So what I write is, as x approaches that asymptote, plus, a little plus up there means it's coming from the right. The function itself, f of x, approaches infinity because it's going up forever and ever, increasing without bound. And this one is on the left side of my asymptote. So I say as x approaches a from the left, then f of x approaches infinity. It's still going up, but I'm on the left side of that vertical asymptote. So I kind of was preparing y'all for this when I was having you write points when we were talking about functions in chapter 1. But this right here is known as arrow notation, and you've got to be able to do that when you do your homework. Now this vertical asymptote increases without bound, okay, as x approaches a. Well, a vertical asymptote could also decrease without bound. So if you can see, these two are going down. This one is going down as they approach the asymptote. So it's still on the right side. So we say as x approaches a from the right, f of x, my function, is going towards negative infinity. And on this side, it's on the left. So as x approaches a from the left, that's why it's got a negative sign up there, then f of x approaches negative infinity. Again, it's going down. And again, this is our arrow notation that you need to be familiar with. Okay, now where do we find, or how do we find those vertical asymptotes? You're looking to make sure, first of all, that you have no common factors. And then if a is a zero of your denominator, meaning if it makes it zero, then we know that x equal a is going to be a vertical asymptote. Okay, now you do need to know that if there is a common factor, then that's where you're going to have a hole in your graph, and that's going to correspond to x equal whatever that number is, and you'll see as we go through. Okay, but most importantly about a vertical asymptote, whatever is left in the denominator after you simplify it, that's where your vertical asymptotes are. That's what you need to remember from this slide. So look at this example. Find the vertical asymptotes. So as we said, okay, you try to simplify it. F of x equals x over x squared minus 1. Can I simplify this? Does the top factor? No. Does the bottom factor? Yes, it does. It factors. It's a difference of two squares, so it's x minus 1, x plus 1. Okay, so those are our two asymptotes. Okay, that's the easiest way to find them. Now, if we go look at the graph here, okay, this right here is, well, let's go with x minus 1. So that first one, x minus 1, is going to be x equal to 1 because you set it equal to 0 and solve. And so they did that, and whatever. And then x plus 1 is going to be this guy over here on the left. So look at this arrow notation. As x approaches negative 1 from the right, that's this side right here. Nope, yes, this is negative 1. As I approach it from the right, so I have to be on the right side of the asymptote, what is my graph doing? It's going up to positive infinity. Okay, well, here's my asymptote. As x approaches negative 1 from the left, what's my function doing? Well, as I go towards it, my function is getting closer and closer to negative infinity. So you ought to pause, see if you can do those next two, and then pick it back up. Okay, so this one I'm looking at x equal to 1. As x approaches 1 from the right. So from the right, my graph is going to positive infinity, and from the left, my graph is going to negative infinity. So that's how we answer that. Okay, look at this next example. Find the vertical asymptotes of the function, if any, of the graph of the function. Okay, so they have already got this factored for you. But what you do have to remember, okay, is that there is a common factor with an x on top and an x on bottom. And if I have an x on the top and the bottom, it's not a vertical asymptote. It's actually a hole at that point. But what's left in the denominator is x plus 3. So we set that equal to 0, and x equals negative 3 is going to be the asymptote of my function. That's what it looks like. Okay, there's a hole right there, but you can't see it because it's so small. But if you zoomed in on the graph, you'd be able to see it. Okay, one more example. Find the vertical asymptotes, if any, of the graph of the rational function h of x equals x minus 1 over x squared plus 1. So does this simplify? Can I factor x squared plus 1? That is not the difference of two squares. It is the sum. So it does not factor. But if I try to set this equal to 0, then I will find out that x squared equals negative 1, which means x equals plus or minus I. Well, that's not going to happen on a real graph of real numbers. So we have no vertical asymptote. And that's what your graph looks like. Okay, last thing I got to talk about is finding horizontal asymptotes. Okay, so horizontal asymptote, before we were x approaches a, and now we're talking about y approaching b. And it will be a horizontal asymptote if the function approaches b as x increases or decreases without bound. Okay, so if you look at this first picture, okay, it says as x approaches infinity. So x is getting bigger and bigger and bigger and bigger. The graph is getting closer to b. Okay, and on this one, all right, as x approaches infinity, doesn't matter. I'm on top of the graph or I'm on the bottom of the graph, or if I actually cross it. Okay, so horizontal asymptotes actually tell us what happened at the end of the graph. So you can never ever cross a vertical asymptote, but you can cross a horizontal asymptote. Write that on a piece of paper. Bring it to me. Get a piece of candy. Okay, that's your arrow notation again. All right, so look at how do we find horizontal asymptotes. Okay, so the key is that you're always going to look at the degree of your numerator, which they're going to call n, and the degree of your denominator, which they're going to call as m. Okay, so these are words which I think are a little bit hard for people to remember. So there's some cute little mnemonic devices to help you remember. You're still looking at the degree, okay? But this says, the first one says n is less than m. And so you've got to remember what that means. But another way to remember it is the word BOBO. And BOBO stands for if it's bigger on bottom. And that's what this says. This says that the degree of the bottom is bigger than the degree of the top. Okay? If it's bigger on bottom, the asymptote is always y equals 0. This one says they're equal. We call that Betsy. And Betsy stands for bottom equals top. And if the bottom equals top, it's the coefficients, which is what this says right here. Okay? So I write it like that. But the C is letting you remember that it's the coefficients of those leading terms. Okay? And the last one, we had bigger on bottom. It's always 0. So this last thing is kind of telling you bigger on bottom is 0. Bottom equals top is your coefficients. And this one I call bot B1. Okay, and bot B1 says bigger on top by 1. And if that's the case, it has no horizontal asymptote. Okay, so just a few examples and then we'll be done. Find the horizontal asymptote if any of the graph of this rational function. Horizontal asymptote. I am looking for the degree. So the degree of my top. The degree, y'all, is the highest exponent that you see on the top, and that's a 2. And the degree on the bottom is a 2. And that means that I have Betsy, and Betsy bottom equals top means I use the coefficients. And the coefficients of these two terms that you used the 9x squared and the 3x squared. And so your coefficients, your asymptote is going to be y equals 9 over 3, which becomes y equal to 3. Which means with arrow notation, how do we say something is a horizontal asymptote? We say as x approaches negative infinity, then f of x approaches 3. As x approaches positive infinity, then f of x approaches 3. And here is your picture of the graph. So again, as x gets bigger and bigger, it gets closer to 3. And as y gets bigger and bigger, as x gets smaller and smaller, it still approaches 3. That is the definition of your horizontal asymptote. Okay, look at this one. Find the horizontal asymptote of any of the graph of the rational function. So again, I am looking at the degree. The degree of my top is 1. The degree of my bottom is 2. So I have bigger on bottom, which is BOBO. And BOBO means it's always y equals 0. And here's our graph. Okay, last example. Find the horizontal asymptote of any of the graph of the rational function. Again, look at the degree. The degree of my top is 3. The degree of the bottom is 2. It is bigger on top by 1, bot B1. And that means it has no horizontal asymptote. And there's your graph. So I hope you write down in your notes how to find that vertical asymptote. You simplify the denominator and find out what's left in the bottom to make it equal to 0. And for horizontal asymptotes, you got to remember Betsy, Bobo, or bot B1.